My name is Clemens Fastos. I'm technical lead for the .NET Service Bus. And after yesterday's session, where I give you sort of the broad overview over the friendly programming model, we're now going to go a level deeper and look at some protocols and how we're doing particular things and how you can actually build applications that probably don't use our programming model directly, but how you can integrate with the service bus and listen on the service bus without using our TCP connections, but rather through HTTP. So I'm going to walk you through a little bit of information on how our binding stack is designed. I will then go and explain to you a few of the protocol details of that particular HTTP mode, which I haven't explained in the last session. And then I'm going to show you an example of how to do this very simply with REST. Then I'm going to show you what our partners have done, working very closely with us. We had Chakra, who has been implementing a Java implementation of our API. It's not a full implementation yet. It's a partial implementation that's using that exact protocol that I'm going to explain. We also have, and I'm not going to show that in this session, but you can go and download that from the respective website, which is linked off Azure.com. We have a Ruby implementation for that as well, which is using the protocol that I'm also going to show you. That was produced by ThoughtWorks. And then towards the end of the session, I'm going to show you some of the deeper details of our security integration with the access control service and how you can secure relayed services using the access control service and evaluate your own claims. And then finally, I'm going to show you a little bit. I'm going to lift the lid a little bit and show you how we scale back in the data center. This worked until it's just slow. Okay, so our .NET services are one of the higher level services that are part of the Azure Services Platform. And so .NET Services is what I'm talking about. And obviously, I don't know how to operate this thing. Now I do. Okay. So let's do a little recap for those who didn't attend the previous session. The service bus here is a combination of capabilities that we're building which allow you to build your own service bus. A service bus is not a product per se, but it's a pattern that you can apply. We're giving you pieces to build your own service bus for your applications. So we're giving you a federated identity and access control system that is composed of our access control service and an identity provider that's provided by LiveID or that's provided by yourself and bridged through, for instance, Geneva or other products which support the WS Trust standard. We have a naming system, we have a service registry, we have a messaging fabric. These are the things that we call the service bus, the features that I'm talking about. And then we have service orchestration in the form of workflow. And those things are all designed to federate with your on-premises ESB, with third-party services, with the services that you're building, so you can expose them all out on internet scope, so your services are easier to reach. The connectivity challenges, just a little recap. What we're doing here, we're running out of IP4 addresses. We have already run out. So one of the biggest challenges is connectivity, creating bidirectional connectivity. Everybody by now is getting dynamic IP addresses in their homes and also in small businesses. There's network address translation going on, which makes endpoints hard to reach. There's several workarounds that people are doing, and the service bus is bridging that gap, making that connectivity easier by creating outbound connections that have rendezvous points up in the cloud, and you can talk to those rendezvous points and then overcome those limitations. So from here on, we're going to start drilling down into the service bus, and you've seen that slide too. These are the bindings that we have. This is our WCF programming model for the service bus. And if you're familiar with WCF, there's a basic HTTP binding, and there's a matching basic HTTP relay binding, and those have, from the client perspective, the exactly same characteristics as the bindings that we have in stock WCF, and they're actually, if you turn off access control in the service policy, they're actually wire compatible for the HTTP case. From here on, now it's new material. Underlying those relay bindings are 4 primitives: HTTP relay transport binding element, HTTPS relay transport binding element, the TCP relay transport binding element, and the one-way relay transport binding element. This is the real delta between the WCF implementation of those bindings and these new bindings. So what we've basically done is we took the stock WCF bindings and slotted in a new transport. The rest of the stack is basically untouched, except that we've taken out a few capabilities that don't make sense. So there's a few properties that we don't support. Otherwise, the stack is completely symmetric. So the WSHTTP binding and the WSHTTP relay binding both support the reliable session binding element. So you can create RM sessions with reliable message delivery over the relay, because that's something that's layered up on the stack. We fully support the symmetric security binding element in this case, which gives you full W star security over that connection. This is how you can secure your messages and in an end-to-end fashion. There's a text message encoding binding element, which writes the messages down on the wire as text. And again, that's layered over the stack in the same way. The HTTP on the left side, the WSHTTP binding is using the HTTP transport binding element, which under the hood is using system.net web request for its client channel, and it's using system.net HTTP listener for its listener. This is how the relationship is built to HTTP sys. The HTTP relay transport binding element uses the exact same client channel. So all the HTTP bindings, in fact, talk HTTP on the client side. So they don't use any funky socket modes. They use that. The listener is using our internal socket binding, what I've been showing in the previous session, what I'm going to show again, to create that relationship between your service and the cloud listener in the same way that a local service has a relationship with HTTP sys. So let's recap what we saw yesterday on how the one-way unicast TCP mode works. We have a receiver. The receiver goes and creates an outbound bidirectional socket connection and registers at a name up in the cloud. And that's the name by which that connection is going to be known. We keep that socket alive, and actually if that socket breaks, we will reestablish that socket under the covers for you. That socket will also survive closing your machine or reopening your machine, because we then sense that we're offline, and we're going to reestablish that connection for you. But while you're asleep, of course, your endpoint goes away. But we're going to keep that open, and that's mostly for subscribing to multicast events. We're opening that connection on port 828. That's a port that we need to have outbound. That's important to note. We need, for those socket modes, we need to have a set of TCP outbound ports that we rely on, because we need to create socket connections. Those port numbers will change once we get a registration for those port numbers with the Internet Assigned Numbers Association. So we're going to change them. We're going to move them out of that space, and we're going to move them into a registered space so that they're well known. The sender will then, in the one-way unicast TCP mode, connect to port 808 or port 828, based on whether you send clear text or SSL. And then that message is being routed into the fabric and then routed down that open socket that we keep. There is no need for any inbound ports to be open at any point in time. That's the whole point of this infrastructure. So outbound ports, we need to have a few for the TCP modes. Inbound ports, you never have to open. So the listener socket connection is very similar in nature to the NetTCP binding that we have in the normal .NET framework in the Windows Communication Foundation. It's a full duplex communication path. We use .NET framing, .NET binary encoding on that path. This is what the NetTCP binding uses. So it's a very efficient mode that we have here. And we will always connect to SSL. The back channel means that your listening connection is always protected by SSL. The sender socket connection is, as I said, is using the same binary communication mode, so it's using the most efficient encoding, and it connects to port 808 if you don't use SSL, and it connects to port 828 if you use SSL. This choice between using SSL or not is made on the security configuration element, where you can choose the security mode is either message or transport or none. If you choose transport, we automatically select SSL. If you choose message, we choose open, and then you have message encryption that's flowing in the clear, but nobody can look into your messages due to the use of WSecurity. Now it gets interesting. This is the part you haven't seen yet. Knowing that outbound ports are closed in many cases in tightly managed corporate environments, we need to have a way to get around that limitation. So we can't always rely on those ports being open. So what do? We use HTTP. Because it's really difficult to stop HTTP anywhere, because it's pervasive. So we have to have a way to go and use HTTP for this. The receiver will go and create a little message buffer. The number one question that I got yesterday was, do you have a queue? Yes, we do. We don't call it that way, though, because when I say queue, you build up expectations about the reliability of that queue, which I can't fulfill yet. But here's a little bit of a queue. So the receiver goes and creates a little buffer for itself that's hosted up in the cloud. It then goes and subscribes to endpoints up in the fabric, and those messages arriving on those endpoints get stuffed into that message buffer, and then we pull them out. So here's how that works. And we're going to see all those. So I'm going to walk you through this, through those slides, and I'm going to show you that with an example. The receiver goes and talks to one of those endpoints and gets load balanced over them and sends a message, and that's a just normal text SOAP message or a REST request, where it sends a message to that relay HTTP listener. If that has the right information on it, it needs to have a process at header. The process at header is basically saying this message is not supposed to be routed through to a receiver, but is actually to be processed at the relay. And then you need to bring a relay access token. That's the token that's required for letting you in. And then you use the create message buffer operation. If you bring all that data, we're going to route you to, instead of going this way, which goes to the socket forwarder, we route you to the protocol extender for the message buffer factory. And that message buffer factory is then going to go and create one of those little message buffers for you. So after that message returns, you have a queue in the cloud. We're scaling the access to the message buffer that you created is scaled out using our normal HTTP mechanisms. So the receiver, the receiving side now sits on the other side just because the slide worked better that way. Now goes and does an HTTP request, a control request, or trying to get messages through any part of that fabric, and then we route that request to that message buffer structure, just as we do that for all the other HTTP requests. So for all practical purposes, the message buffer is really an HTTP service like all the other HTTP services what I discussed in the previous session. What you do then is the message buffer really is a thing that acts on your behalf to manage subscriptions. So it's a multiplexing connection that allows you to basically subscribe anywhere in the namespace into this message buffer, and then gives you one place to actually go and pull all those messages out. So you send an HTTPS request, subscribe, or a XSubscribe HTTP request up to the message buffer, and the message buffer then goes and creates a listener on your behalf, hooking that up into the fabric. From that point on, you can send messages to it. Those messages land up in the message buffer, and then you can go and retrieve them. Submitting into the message buffer, so sending in, is very simple. You send messages out to whatever endpoints you subscribe to, and those messages get routed. So it's all a multiplexing connection. If you build your own implementation, so this is what we do, right? We create one message buffer per app domain, and then we multiplex everything into that message buffer, and then we dispatch locally when the messages come down. And the reason we're doing this is that RFC 2616 says, you shall not have more than 2 active connections from within one scope through HTTP to one domain. So we're trying to be very, very spec compliant here, and we say, okay, so we got to constrain the app domain to exactly one polling connection. So this is why we go and multiplex everything. If you were building your own implementation of this, you can do it whatever you want if you tune your client parameters right. So you need to go and tell the system.net web request stack, and that's done through the service point, what your maximum allowed connections are, and then you can release that throttle. Since I'm not in the business of controlling your environment, I can't do that. But you can open it up, and then you can go and just build your own client for this particular protocol, as the partners have done. Polling, and so now this is what this is really for. With HTTP, I don't have that socket that I can throw stuff through. So I need to do polling. So the polling protocol goes and sends a request, retrieve messages, or it sends an X retrieve request via REST, and we give some parameters with it, which are the timeout. How long are you willing to wait for the next batch of messages? That request is parked up there. We give you at most 30 seconds. So you can dial that up or down, but we give you at most 30 seconds, and then we unblock the request and come back to you with an empty response if nothing is there. You can specify the encoding. We have several encodings available, and the maximum number of messages that you want. So that request goes, your polling request goes up, is parked there, sits there, and waits for a message to arrive. As soon as the first message arrives, we unblock and send that back to you and bring all the messages along with you. So this is the details of the response. The response encodings we give you is for SOAP. We give you a bare envelope sequence, which is the body element just contains SOAP envelopes. So it's an envelope with an envelope. So we give you at most 10 messages. And that's a constraint that we currently have hardwired in the system. We are looking at how to, whether we're going to make that bigger. A wrapped envelope sequence is basically the same, but the body has another wrapper element inside of it, which is the request retrieve messages response envelope. And those two things just exist because of a particular wish of our partners who were doing the Java implementation who didn't want to have that wrapper element. So I said, okay, so let's make another coding. On the HTTP side, we can give you the actual exact HTTP request that came in. So assume it's a one-way HTTP request. We give you back a 202, thank you. We're not going to give you back anything else. So this is all one-way. This is a one-way mechanism. But we can give you with the my multipart, we can give you a sequence of those exact requests, and they're encoded as application/HTTP. If you look at RFC 2616, about the last line in that spec says the MIME type for this is application/HTTP, and that's a full HTTP request. So I can give you that exact thing. So my multipart is a my multipart message sequence containing application/HTTP. You can choose MIME application HTTP, where I'm basically giving you in the response body an application HTTP, and I'm only giving you one message. And the simplest mode is request as response, where I'm mapping the incoming message on the response, and you can also only get, one message. And then there's the message buffer is a volatile thing, which means it lives for 30 minutes at most, unless you go and renew it. This is one of those things that differentiates it from a queue. So you have to renew it. You can get the status, meaning when does it expire, and you can also go, of course, and delete it. So that's the protocol details. We tried to build a little protocol that allows you to create a listener from anywhere, as long as you have HTTP. So I'm going to show you that little protocol in action here. So this is basically exactly doing what I've been showing you. I'm acquiring a token. I go and just made up my own URI. So I go to my namespace, Clemens v5, and I'm actually creating this based on a GUID. So this is my little new message buffer that I'm creating. X_create_MB, I'm setting the X_process_add header, and I'm setting the identity token. So this is the REST path. I'm executing this. I'm getting a response back. The response contains the actual endpoint of the manager I just created. Now I can go, with that manager, I can go do an X_subscribe. I'm creating a new listener somewhere in my namespace. And that sits at Clemens v5 MB one way. And then I can start sending messages to it, just again with normal HTTP web request, to that endpoint URI that I just created. I'm just writing some XML to it. And then I can go and start pulling the message buffer and basically just get the messages out, and then I'm going to print them out on the console. And as you'll see, I enqueue 7 messages, I enqueue 6, I dequeue 7, so the last message will be waiting a little longer, and then return with an empty response. And then at the end, I unsubscribe from that endpoint, which means I destroy that endpoint that I just opened, and then I delete the message buffer. So let's run this. So it goes and acquires a token. One shall hope. Of course, now it's not up. So there it goes and enqueues them all. Here it goes and gets them all. And this is pure HTTP. We're relaying without SOAP envelopes, without any trickery. It's a pure HTTP request that gets routed through the fabric. And you can open endpoints, you can subscribe, all those things. You can listen to them just using pure HTTP. Kind of cool. Now, while we're at it, someone else wrote an implementation using the SOAP protocol version of this. And our friends at Chakra wrote a little chat application. And what we're going to see here if I do everything right, it's going to take a little while, just mostly because of bandwidth constraints. Okay, while I'm talking, I'm going to let that run a little bit, and I'm going to show you what that is written in. This is NetBeans, a wonderful product built by our friends over at, or sponsored by, our friends over at Sun, who have been collaborating with us very tightly over the last few releases on making interoperability work better. And for that, I would like to thank Sun Microsystems. We've been doing a lot of, we've been making a lot of progress in making the interoperability work. And then our partners at Chakra picked this up, and here we go. Now I'm logged into the system, and they built this chat. I could start 2 of them, but I'm just going to show you one of them. I can join a room, test. And now I'm actually sending messages out to the service bus. I'm getting messages back from the service bus. And I can join that room, and then I can talk to that room, say hello. So they built basically a little version of IRC based on the service bus. If I was running multiple instances of that, you would see that they all communicate through the multicast protocol. So that's what we've seen. That's the demo that you didn't see yesterday because that one crashed on me. Or, well, no, I was too stupid to run it. Let's put it this way. So that's a little chat application, and that chat application is now communicating through the service bus. If you don't believe me, go and download the bits. They are j.netservices.com, I believe, or .org. And that's where they put them. The source code for all of this, the source code for the Java project, lives on SourceForge, I believe under that same name. So what you will find, there's two packages. You will find the chat application per se, and then you will find there the whole j.NET Services project, which gives you the entire source code for that entire client. The client is running with security by default, so I can't even trace it. They're using HTTPS. They're using WSTrust to go and acquire the token. So they're basically doing what we do with all the published protocol support that we have. And that's very nice. So the only thing that's currently, so you see all the messages here. There's a renew message buffer, delete message buffer, so all the messages that I explained to you. And then here's the receiver, and the receiver goes and uses this retrieve messages, the retrieve messages protocol to go and retrieve the messages out. They provide the respective parameters. They get a bunch of messages in the content. This is where they get the bare envelope. And then they parse those messages out. They read the relay via header, which we inject into the message, which says this is where this came from, so that they can go and locally dispatch the message. And they're doing exactly the same thing that we do. So Java stuff working for one way and net event. Now they have something special in here, which I'm going to show you a little bit later, and that is they can actually do two-way over one-way, because they've composed the two one-way connections into a composite connection that will allow you to do two-way. So you can listen on HTTP, and you can send out an HTTP, and you can make an end-to-end connection using those two modes. The same application, and so I'm making up my debt from yesterday. Effectively the same application, even though simpler. The folks at Chakra did a really good job, much of a better job than we did. The same chat application is sitting here, and this is the multicast sample that we have in the SDK, and that multicast sample is now also doing a chat room. Again, I could add another instance, and you would see it would work, and you can test that at home. And if I go and I should close this gracefully. If I look into that code, you see our version of the programming model for this, where I'm setting the service bus environment, I'm setting the one-way connectivity mode to HTTP. If I set that to HTTP, we're switching into this HTTP polling mode. There is another mode that's called auto detect, which will switch between TCP and HTTP as it finds the connections working or not working. So in auto detect, it will go and probe the connection to the cloud, and if it can do TCP, it will do TCP. If it can't do TCP, it will try HTTP. That's what auto detect does. And then we just basically provide our we set up our credentials, and then if that mode is auto detect or HTTP, one of those two things, I need to provide, and so this is sort of a little template that you need to use. I need to provide the HTTP mode relay client credentials. These are the credentials that are used to actually create that message buffer and to maintain it. And we automatically renew it as needed. And then the second thing is the HTTP, the message buffer location, which you have to set yourself because I can't figure it out from the environment. Because you provide your credentials, you have your solution ID, and there's nothing I can do to make that easier. So, at least not now, I haven't had an idea yet. There's this HTTP mode message buffer location. You basically just set that to a URI that lives somewhere in your own namespace. So the simple approximation that I'm currently doing is I'm taking the solution name and I'm setting a GUID, and that should be good enough for everything. And so that's your solution ID. Once you set that message buffer location, as soon as you open up the first one-way listener or an event listener, we're creating that message buffer for you, and then we multiplex all further subscription into that thing. So that's all happening automatically under the covers. And what I just ran also ran through the message buffer, so we now saw 3 examples of that. So this is as open as we can. This is probably as open as we can be about doing HTTP protocol. You got the protocol documentation is in the slides. We're going to make that protocol documentation available. I believe that also Chakra and ThoughtWorks are exactly documenting their use of the respective APIs, and we have coverage there for both REST and SOAP. So if you are inclined to build your own client stack, your own client implementation, not use our particular implementation, you're surely invited to do so. Thank you. So the TCP mode, always sockets. HTTP mode, always the message buffer. Connectivity mode, auto detect, switches between them. Now, composite, so I said the Java people have done composite duplex, effectively taking a pair of one-way connections and made them into a two-way connection. We can do that too. It's a composition with the binding primitives that you can do very easily for yourself. We used to have a mode in a previous release when we were still called BizTalk Services that had a mode that made that automatic. We didn't include it this time because we also want you to be able to compose this in a different way. You may want to do one-way multicast, multicast one-way, 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 multicast, multicast, where you probably want to build a mesh. And you can do that very easily if you compose that one-way element correctly with a composite duplex binding element. And composing this is so easy that we thought you can probably do that yourself and gain that flexibility. So what we do here is we build a custom binding, and there's a standard binding element that's shipping with WCF called the composite duplex binding element. And that is doing all the magic. That it's also horribly under-documented, and I apologize. What it does is it takes 2 one-way channels, it makes one a client and one a listener, and has a correlation mechanism inside that will go and match up the right messages. So you can do duplex over it, but you can also do request response over it. So whatever the service model, meaning the upper layer of the stack, makes out of it, it's up to the service model itself. So you can do request response, or you can do a duplex contract. The composite duplex binding element can create both of those. So you can use the one-way relay transport binding element and basically just compose that, and then with that create a duplex connection over one-way. So let's go and look at that. This is the one-way duplex solution. Let's go and activate the service. We're going to look at the service first here. So what the service does is it's basically the echo sample as it comes with SDK, with the addition that there's a create binding where we don't read the binding from config, but here I'm creating it explicitly, where I'm creating a custom binding, and then I'm adding this composite duplex binding element to it. I'm setting the client base address, and client base address in that case means what's the address that the server will be talking back to. That's something you set on the client, and the client will then tell the server, hey, when you have a message for me, come this way. And then I'm adding the binary message coding binding element, and I'm adding the one-way relay transport binding element, which then sends it to the relay. The rest is mostly the echo sample as it ships in the SDK. And by the way, you will see all those samples that I'm showing here with additional nodes showing up on my blog, and those will be likely then linked from the Dev Center or the portal. So this in particular, because that's an interesting trick. Now, the reason why I'm telling you this is obviously, if you need to have a duplex connection, and the only thing you have to work with is HTTP, you take the HTTP mode for one way and then create a connection like this. So that's what I'm doing. I'm going to start the service. And then I'm going to go and start the client. Oops. It's kind of hard to tell which is what, because I didn't close this. That's the client. So client is up, server's not yet up. At least so it says. Shall we risk it? It's funny how that goes. There it is. So, so this just created one of those composite one-way connections. We're not doing the NetTCP relay, but we're doing two one-ways, combine them, and the messages go through the relay like that, and you can combine that with the HTTP mode. So with that, you get the maximum NAT traversal mode that we have, which is really hard to stop because it's using HTTP and HTTPS. So, one-way guidance. When should you use this? If you need event distribution, that's what the multicast samples show. If you use that, use those. If you need to have that very aggressive NAT and firewall traversal mode, if that's something that you see on a regular basis, use that. The drawbacks are that the maximum message size is currently constrained to 60 kilobytes. That includes the token that we slot in, which is about, depending on how big the token is, maybe ranging between 3K and 6K. So this mode has a small message size. That is not a permanent constraint, but that's a constraint that we currently have. It's actually constrained because of a bug. That's one of those things where my heart was hurting when I had to say, let's punt this to the next milestone, but we had to. There's also a constraint, and that's very deliberate, where we're constraining the maximum message buffer size to 256K. Again, that's a constraint that's for the CTP, and we're going to work on that. I don't want you to use that thing as a queue. This is a testament of that. I don't want you to use that thing as a queue. Therefore, it's very short. It's really for you keep polling and you keep relaying those messages. It's not a queue. I'm not saying it won't be a queue, but it's not a queue. Good. You should always prefer the TCP modes because you get a lot of higher message rates. The message rates you can get out of that one-way mode is in the tens of messages per second, probably lower, depending on what your latency is. Out of the TCP connection, as you probably saw yesterday in one of the demos, you can get hundreds of messages per second. So you should prefer that mode. So that's the TCP relay mode that I talked about. I'm going to click through that rather quickly if it lets me. Let's do it this way. So we have this. I just want to talk about those things once more, just to illustrate the ports. So let me go and click through this. For the TCP relayed mode, we need another port open. That's port 818. I'm bringing those modes up again, mostly so I can give you guidance about them. I talked about them in the previous session. So let's go to the guidance. Preferred communication modes for everything. You should, in doubt, prefer NetTCP relay binding because it's the fastest that we have. It's got the most compact wire representation. It's got the most efficient communication mode. And you're literally getting a socket that's being knitted up in the cloud. And we don't even know what the message delineation is. once that socket is established. We basically just wire up a bit stream, and that bit stream is relayed between the two places. And then there's a socket infrastructure underneath on the client side, which the transport sits on. And I would be interested if you were interested, and that's something that you can give me as feedback in the forums or elsewhere, that knowing that there's a socket connection underneath, whether you'd be interested in getting your hands on those bytes more directly than you get now. For that, I encourage you to play around with that NetTCP binding and just think a little bit along. So outbound ports, 808, 818, 828. One important caveat is we don't support WAS yet. So you can't host listeners like this in IIS. Sorry, it's on the list. We're going to get there. So you can't do that with the standard NetTCP binding. You can't do that with ours yet. It's actually not too hard if you look at the standard WCF SDK to actually write a WAS activator for this binding. We just haven't had the time to do that yet. And this is also not necessarily bounded by our ability to do it, but also by test costs and packaging those things up and documenting them, etc. The hybrid mode that I talked about, this is the magic with NAT probing, where we go and figure out a NAT port and then create a NAT traversal connection that's direct between those two. And then as we're able to create it, we're going to upgrade. The guidance around this is you should prefer this for any large peer-to-peer data transfers that you're doing. This is what Messenger uses peer-to-peer, because you don't go through our data centers, especially if you are if you're not in the United States. That's probably the mode you want to go and prefer. You will have a little bit of a startup cost. You will see that the connection gets a little slow as the negotiation goes on, but then usually recovers. No, it will recover, independent of whether we can or cannot go and create our connection. The reason why you want to prefer this, especially if you're outside the United States, is latency. Because if you're creating a connection, let's say within Germany, you would have the latency towards our data centers. And of course, we're going to be building those data centers out across the world. But until we get there, and that's not the case yet for the PDC CTP, which lives in one data center. As we get there, if you're playing with those bits right now, you can get better throughput out of this relay, out of this infrastructure, if you use the hybrid mode and then establish local connections using this NAT traversal trick. The success rate for this binding, for the establishing that direct connection, is decreasing the more busier the NAT device gets. So if you're in a corporate environment behind a very busy NAT device, even though we try to really tightly time that whole NAT traversal dance, it's likely that our predictions are wrong. We will try several times to get it right, and we'll keep trying. But if the NAT is very busy, we often fail. But then the backup is always the relay connection that you still have. Another bug is that you can't use this with a certain set of channels. The WSRM channel, so the reliable session channel, and the WSecurity channel, if you do duplex connections, they create a second channel on the side. So they create, and that's the standard behavior of those channels. They create with your same connection parameters, they create a second channel. Both of them do. Now, if you think about what that means, is now we have two connections from the same place trying to do that NAT guessing dance all at the same time within that same narrow time window. And of course, that's all not good for getting anything working. And we have seen instances of where that actually deadlocks. The work that we need to do is we need to stop one of those or two of those guys from doing this until the first is done, and then we can let the other one go. The code is there. I had it done 3 weeks ago. That was after the lockdown. We had to punt it to the next milestone. So that's bugs, but we know how to fix it. HTTP, talked about how that works. We're going to go and go relatively quickly to this again. Again, we have this rendezvous socket forwarder. You do an HTTP request to that socket forwarder from the client. The control message gets up there. It says, hey, there's a request waiting for you at a particular relay node. And then you go and pick up that request and serve that request. The HTTP mode is doubtlessly the most interoperable option for clients. It's effectively a reverse proxy for HTTP. That's really what we're doing. And that's also how it behaves. I mentioned briefly yesterday that there's some scale implications because of this reconnect, basically that we do the rendezvous connection, even though we cache connections. The sheer scale of our fabric will cause us to not be able to reuse many of those connections. What we're going to do is we're going to scope the fabric down for individual solutions so that there's not so many nodes that are actually looking down at you or you're looking at, so that we can reuse those cache connections more efficiently and you basically get higher throughput out of it. So this is why I say significantly higher stress for your service compared to the NetTCP relay binding, which you should therefore prefer unless you need HTTP. Let me make that a little more clear. You should not run a website through this. That's not what it's designed for. In the limit, I can see that happening. And our lead architect has actually written a little Cassini server for this. He basically just hooked that up. And obviously, we're also looking into whether we can plug that into IIS. But that's ways out, and that's probably not going to be V1. So WAS activation, yes. IIS integration, I don't know yet. We'll try. And also, the WAS integration is easier because there's a plug-in point for this. The IIS integration is harder because there's no extensibility. You can't rip and replace the HTTP transport from IIS because it's built into the operating system. Whatever is built into the operating system is, if it doesn't get onto the Windows 7 ship, which sort of is already left the port, then it needs to get on the next Windows ship to get those things really integrated. All right, so access control deep dive. Doing good on time. I had shown you a diagram in the previous session. It's not so important that you acutely remember what that looked like, of how the access control integration works. I have a solution that I took and changed a little bit. There's a sample called the calculator sample, which is the getting started sample of the access control portion. That's basically the same sample here. So there's a simple calculator service, and the simple calculator service has a few functions: add, subtract, multiply, and divide. And I just followed faithfully the steps of how to set this up. So here's my access control portal. And so I just set up those claims, and I'm sorry that that's a little small. Let's go and zoom in on that piece for a moment. So I added those input claims, which basically says, if Clemens v5 comes around and calls this service, it's okay for him to call multiply, it's okay for him to call divide, it's okay for him to call add, but I've disabled the subtract method. This is what I configured as rules in the access control portal. So what is happening with those rules? My application is using the STS twice. There's this relay token. So I need to go and acquire a token to send messages to the relay and to listen on the relay. Those rules sit in another scope where I hope that it will let me. And that is in the service bus scope, here, I get provisioned, and this is what you get when you sign up and you provision your account. There's automatically a scope created, or better, delegated to you from the main service bus scope, where you can manage your rules. So by default, I, as the owner, have rights to listen and send on the service bus. This is how you manage access to your namespace. Nobody else can. You can go, and this is something that you will read in the documentation, or probably already have seen in the session that Justin Smith gave, and you can see you can look at the recording. You can go and manage your also your federations here. So you can go and grant access for live ID identities, for Geneva identities, for all those things. So you can basically just create those rules here. So whatever is under service bus are the base rules for access to the relay, listening and sending into your solution namespace. I now overlaid another namespace of my STS. So this is the STS that the service bus owns. And you get delegated, you are delegated administrator permissions for your namespace. The scope that I created is in my application, in Clemens V, which is an STS that I own. So you get two things. You get delegation control over the relay namespace or the service bus namespace, and you get your own STS, which you can go control. And you can actually overlay a second set of rules for any individual namespace, and this is what we just looked at, where I have rules. So let's look at the service. That's the calculator service. It has those actions. These are the calculator.add, .subtract, .multiply, .divide. The interesting thing here is the configuration, and it's a tiny little bit intimidating, actually. What we use here, and that's the main difference to the binding that you see in the calculator sample that's part of this, is and I'm very sorry about it, the WS 2007 Federation HTTP relay binding. That's the binding that's matching the WS 2007 Federation HTTP binding, that's part of the .NET framework, and which has a built-in mechanism to go and request a token, take that token, use that token for a secure channel. So we've cloned that binding and made that intelligent about the access control service, and made it intelligent about going through the relay. You can use that actually with any STS. Since I just happen to have an STS up in the cloud, I'm using that. But you can use this binding with any other STS that you have. So what I'm doing here is I'm saying, hey, the security mode is message. I need to have issued tokens issued by my STS. So this is my STS that I'm now getting tokens from. And I'm providing username credentials into this, and the mechanism for this is exactly the same as the mechanism that we use in WCF to provide credentials. So in my main program, I'm that's in the client. I go and collect the credentials from the console and set them on the client credentials of the proxy, just as I would normally do. No difference. So if you use that with WCF and you set the client credentials, you put that on the client credentials of the proxy or of the channel factory. So there's no difference here. This works just like the normal WCF, but now the STS is actually the access control system. And you remember the rules. I can go and do three things. Let's look at those things again. I can do multiply, I can do divide, I can do add. So let's run this, and let's see whether I can. I have a shortcut for this. Wait, oops. So here goes the service. And here goes the client. Service is running, service is starting up. I'm going to go and log in with my solution credentials because that's the identity provider that I'm currently federating with implicitly. and I'm running. It's going to take a little while because I now need to go and acquire 2 tokens with the constrained bandwidth that I have. And of course, now the cost of my machine is a little higher. But eventually, it's going to come around. I can do a little dance while it happens. I'm pretty confident that it will work. This is why I'm not standing frantically at the machine. Come on. Things may be a little, there it goes. I can't add. I can't divide. I can multiply. And I can't subtract. That's what I disabled for myself. So access control was now governed by the central management in the access control service, which gave me the claims, which only gave me the claims, issued me the claims when I was calling a method that was allowed to call. I flowed the token around, and you can look at the sample. The server will then open that token, look into that token, and say, yes, does it satisfy my claim for invoking this operation? If it doesn't, it gives you an access denied. It just throws an authorization exception. So all of a sudden, you have claims-based authentication, centrally manageable by a rules engine that lives up in the sky, and that can go and protect your end-to-end connection. And in case you're worried in uploading a cert into that access control service, you upload your public key. And that public key only allows you to encrypt stuff, but it doesn't allow you to decrypt stuff. So you always keep the private portion of your key to yourself that sits in the service. So even if you're using our access control service to go and encrypt the data based on that key that we have a part of, we can't get at the data still. So that's that story. We're doing well in time. Now to the interesting part. And of course, this is a talk that takes about 2 weeks. And then once I'm done with that talk, I can't let anybody out of this room again. So I'm going to tell you as much as I can tell before anybody ushers me off stage and says, no, you're telling company secrets. So I've been having all those wonderful graphics with all our front-end nodes and how the load balancing works. Now, the interesting part is how does the back-end messaging fabric work, and how do we do this? Here's the obvious part. We have a sizable corner in a data center with a bunch of racks. Now, we don't run our software directly on those machines. Of course, we're having them all, we have them all virtualized. So we have a management and deployment fabric that we're running underneath, which manages Windows Server 2008 Hyper-V. We're going to move eventually all those things onto the Windows Azure platform, but since we're all working all in parallel, it's kind of difficult to take all those dependencies, so all those things will be moved. So Windows Azure has a management fabric. We have our own interim management fabric, and that's what we're using. But I want to give you a little bit of an insight into how we're running this. So we have 8 cores at a minimum per server. We allocate 1, 2, or 4 cores to the respective VMs, and we currently run 1 service bus node per VM. So we can host between 7 and 8 service bus nodes on those machines. The fabric is built in a way that we're allocating those machines across the entire fabric completely at random. That's really important. There's no linear alignment. We look at the entire fabric that we have, the entire amount of hardware that we have. Everything runs this management fabric, and then we basically roll the dice and distribute them over that fabric. That's a very important part for the next piece I'm going to talk about. There's also a principle that we have here, and that's called the lights out model. If a particular VM starts failing for some reason, we rescue the logs of that machine and nuke it. It's gone. we image a new one and put that in its place. If we see any indication of the hardware failing, we're monitoring that closely, the disk starts acting erratically, or there's any other signs, the lights go out in that machine, we never touch it again. Literally, that machine is taken out of the rack, gone. When you run so many machines, it's not worth actually looking into that machine. If you look at some white papers that are floating around, excuse me? Do we sell them on eBay after that? I don't know where they go. So there's even more extreme approaches, and there's white papers about this, and articles are being written, where we're basically taking a data center into a container, and then have an acceptable failure rate. And once X% of those machines have failed, we basically just say, unplug the container, send it back to the manufacturer, let them refurbish it. But diagnostics on the live systems are just too expensive, and you can't do that at that scale. It means everything is highly replicated, and if a VM fails or hardware fails, lights out, done. So we just rescue all the data that we need for postmortem analysis of what could have possibly happened, and then we just nuke it and next one go. We can deploy 100 VMs, or actually even 200 VMs, it's a parallel process, in about 20 minutes. So we can take our system, the management fabric is deployed, that runs, and we have basically naked machines which have no VMs on them. We can take the entire .NET Service Bus, and the deployment sizes, depending on what we do, vary from a few to many hundred machines. We can deploy that entire fabric in about 20 minutes, have it from 0 to completely up and running, which is kind of interesting. It's quite an achievement that we're pretty proud of. So how does the scaling really work at the back end? Like, how does the message routing work? That's work that one of those teams inside of our division, which doesn't have a direct customer deliverable, they're delivering to you through us. It's called the Service Bus Overlay technology. And the Service Bus Overlay technology is powering the backend that we have. It's a conceptual ring of machines that's completely self-organizing. It's a network overlay technology, that's why it's called overlay. What happens here is that we take all those VMs and we just scatter them around on the fabric, which gives us a random distribution. They self-organize in a way that they build neighborhoods. And neighborhoods doesn't mean that they are necessarily close to each other, but they organize that all into a ring. And neighborhood means they're close to each other for replication. And the ring is completely self-organizing. So you basically power it up and the ring forms. When I go and create a name, when I store some data in it, and Workflow does this, and we do this with all of our naming settings, the stuff that powers the service registry, we stick that into one of the nodes. That data gets replicated across the neighborhood. And it happens with all data. We can take any of those machines and nuke it. And the ring will reconcile, and that data never gets lost. Effectively, we're holding the majority of state that powers the backend completely in RAM. Because we are spreading this all across fault domains, because we're having replication as a principle, because we have fault as a principle, we can rip any of those machines out. The only time when we actually incur loss is if you would happen to have an entire neighborhood co-located on a single machine, you would rip the machine out. So what it does, this backend fabric gives us volatile storage, it gives us distributed naming fabric, that's what you get through the naming system, and it's giving us uni and multicast routing. The unicast routing happens within the fabric, point-to-point, machine-to-machine. The multicast is routed along that ring structure. And again, the ring is just a picture. It's just the concept of it. In fact, it's It's a self-organizing network overlay, and the network overlay is a complete abstraction. We can also, so there's the concept of subrings, and this is a pretty deep thing. We can also take that network overlay technology and spread that across data centers if we wanted to. So we can create one virtual networking fabric which is overlaid over the physical reality of what the data center is. That's a great question. Is that overlay API going to be public? There are thoughts of doing so. The overlay team itself has a strong inclination to make that public. There has been no, beyond us, there has been no direct decision made yet, and the reason for that is that their first priority is us. It's actually you through us, just to be clear. Rescued that one. Are all those protocols custom? Yeah, all those protocols that are used there are custom. And so it's a fabric that's built specifically for scale. You cannot, this volatile storage mechanism, for instance, and this is one of the reasons, the second request, the first request was, when do you have a queue? And I sort of semi-answered that one. The second question is, when do we get that when can I get that on premise, all that stuff? This here is one of the reasons why that's really going to be difficult. Some of the architectural principles that we're applying here only work at scale. So a minimum deployment of the service bus to actually get a reasonable amount of fault resiliency is about 50 nodes. So the question is, if you get that on premise, do you actually want to bring up that hardware? And in very many cases, the answer is, not sure. Not sure whether that's really worth it. So we can build a very highly fault resilient system here because we have the necessary scale. Nevertheless, of course, I wouldn't be talking about this technology if there wasn't sort of a far-reaching intent to actually make that available to you. I just can't say when that's going to be. But Microsoft is typically pretty good at monetizing its IP, so I sort of... All right, so that was this. It was a pretty deep walkthrough on some of the protocol stuff. Oh, yes, wait, stop. Before I let you go, I have another thing. I want to show you one more demo. A little while ago, I published a little sample that was largely ignored by everybody on my blog, which is a full XML RPC stack for WCF. XML RPC is the little protocol that is powering most of the blogosphere. I mean, before AtomPub came around. And so Word supports it, and it's sort of the predecessor of SOAP. To show that the service bus and actually extensibility of the HTTP mode is quite useful, I wrote a little app. So here's an XML RPC server, which is starting up right now, which is hanging on the relay. And so I've opened this up here. There's a little feed. In a moment, that is. There comes the Blogger endpoint. The feed endpoint should show up any moment. Come on. Come on. Ah. Okay, so because the Blogger endpoint is already up, that's pretty encouraging. Now I'm going to use Word and create a new blog post. Hello. To my tiny, tiny service bus blog. I'm going to publish it. It was published to the tiny, tiny Service Bus blog. And here we go. So it's showing up on that feed. Hosted through a Service Bus, using the MetaWay blog API, using XML RPC, layered over our HTTP stack, exposed publicly to the world. See, I wrote that blog, so I had that code left. And I found that an interesting use of a different protocol, in addition to SOAP or REST or anything. And I just wrote that sort of a little bit in a hurry, so it's kind of dirty. But once I'm going to package that up, going to put that on my blog, and you can take it and then go crazy with it. So that's that. More details on those things. We're going to start posting a lot of additional samples in addition to the samples we have in the SDK on our blogs. I hope you find that interesting. We're having a lot of first fun working with our partners to get the protocol coverage right. We're going to do more protocol coverage over time. We're not done with the protocols yet. I think we can even do better on the socket modes. We're going to do more HTTP coverage. And I would encourage you to, if you haven't done so, watch the recording for session BB8, which gives the introduction for this talk. So with that, I think we're open for 5 minutes of questions.
Hi. What will be the unit of pricing for this?
What will be the pricing for this? We haven't announced pricing yet.
No, the unit for it.
Oh, the unit for pricing, we don't even know. Or at least there's, well, that's not true. We're having debates about what the right unit for pricing is. My guess is it's going to be bandwidth plus resource consumption. But probably the high order bit may be bandwidth. But that's just me. So we don't know yet.
Thanks.
Are you sending the complete token, security token in the HTTP header when you're doing the REST?
No. We're acquiring so the token is being issued, but the token is being held by the access control service. The access control service gives you a reference to it that's encoded in base64, and then as you pass that on into our fabric is actually taking that reference, is walking up to the access control service, and is retrieving the actual token.
So is it a hash then, or?
Yeah, that's the hash.
Yeah. Okay. Thank you.
So the XMPP protocol seems to cover a lot of the things you're doing with messaging. What is the rationale for not leveraging this standard?
We're looking at XMPP protocol as an additional protocol option. As said, we're looking into broader protocol coverage. Now, I'm happy to support any protocol I can get my hands on and implement. So XMPP is a protocol that's being used in that area. We're aware of it. There's also a Bayeux for the polling mode, which is more in touch for JavaScript applications. So we're looking at extending this and to support more protocols. That's a simple answer. So it's not a vote against it, not at all. Any more?
Is it possible to scale on publisher side the services over multiple machines?
Yes. So that's a thing that's going to come in the next or the milestone after next, which is called Anycast. So we currently have unicast and multicast, which means you can only have one listener. We're going to support Anycast, where you can have any number of listeners sitting on one connection, and then we load balance across them. That's a feature that's already in the line. We actually have some server code for that already sitting there, but it's not available yet. But yes, absolutely.
So you were saying that there was a I believe, a bug that was stopping reliable messaging and secure conversation, or
Yeah, so in the direct connect mode, so when you do this hybrid connection where we establish a direct connection, that direct connection, due to a bug, currently doesn't support RM or W security, or at least not reliably. So you may experience lockups when the negotiation happens.
Oh, okay.
And that's because we're not blocking them out yet. That's the fix that we have in the pipeline. It works for every other scenario.
Okay. Thanks.
You're welcome.
So thank you so much for the presentation. It was
Welcome.
lots of information. So you are keeping to saying that you are going to post more code, more documentation in SDK. So it will be part of Dublin.
Part of what?
Dublin code.
No. This is part of the .NET Service Bus code. It'll show up on my blog, and we're going to link to it from the Dev Center. So if you go to the Azure Services Platform Developer Center on MSDN,
Okay.
It's likely going to be linked from there.
Sure. Okay. Cool. Thanks.
Okay, I think we're done. Thank you for coming.